All right, welcome to another stats warm-up. All right, so this unit's actually pretty short. So this warm-up is going to go over the two main problems from this unit and how they break down and what you have to be able to do to solve them. So we have an opinion poll that asks a sample of 500 adults. So there's our N, that's our sample size. Whether they favor giving parents of school-age children vouchers that can be exchanged for education at any public or private school of their choice. Each school would be paid for by the government on the basis of how many vouchers it collected. Suppose that in fact 45% of the population favor this idea. So this is your population parameter, which in this case is just going to be a proportion. All right, because we do have the two types of problems. We have means and we have proportions. And this time we're dealing with proportions. So what is the mean of the sampling distribution p hat, the proportion of adults and samples of 500 who favor giving parents of school-age children these vouchers? So again, if you took lots of samples and calculated a proportion for each of them, what would the mean of all of those calculated proportions be? And it's always equal to the true mean or the true population parameter. All right, and the problem gives us that, so it's just the 0.45. All right. Now, what is the standard deviation of p hat? Now, this is one of the ones where our conditions come into place. Since we're sampling without replacement, the sample should be under 10% of the population. Right. Now, 500 adults out of, all adults in the United States is obviously under 10%, so we're fine there. But that's where that condition comes into play. And because we are fine, we can use our formula, which says that the standard deviation of p hat, so the standard deviation of all of those calculated proportions, is equal to the square root of pq over n. Now the problem gives us p, it's 0.45. Q we know is just 1 minus that, so that's 0.55, and n is 500. All right, so that's the formula we would need. That we can just do on the calculator, 0.45 times 0.55 divided by 500, and then take the square root of that. 0.0222 equals 0.0222. Right. Check that you can use the normal approximation for the distribution of p hat. So this result, the check for this is that you have to have 10 successes and 10 failures. All right, so we find that by doing n times p, and we find that by doing n times q. All right, so we've got 500 times 0.45, and we have 500 times 0.55. All right, and you can probably tell just by looking at it that those are both going to be above 10, and you'd be right. The first one is 225, and the second one is going to add to 500 altogether, so that means it's 275. So both of these check out, so we're good. All right, and then what is the probability that more than half of the sample are in favor? All right, so what are the probabilities that you take a sample? All right, so you take a sample of 500 people and more than 50% are in favor of the idea. Well, now that we know that we can use the normal distribution, that's saying what are the odds of getting 0.5 or higher when on average we should get 0.45, but there is sampling variability, and the sampling variability is defined by this standard deviation here. All right. So we've got our NCDF there, and then that's just bringing it over to the calculator. So 0.5, 9999, when the mean is 0.45, and the standard deviation is 0.022. All right, and something like 0.0122 if we're rounding that. So 0.0122 would be the probability of that. So only about a 1% chance. All right, now you might not say to yourself, oh, 50% is not that much higher than 45%. Yeah, but we're taking a sample of 500 people. That's a lot of people. So when you take that many people, you expect to end up pretty close to the actual value. So being that far above is actually pretty unlikely. All right, let's take a look at the back. All right, a certain beverage company is suspected of underfilling its cans of soft drink. The company advertises that its cans contain on average 12 ounces of soda with a standard deviation of 0.4 ounce. Let's probably say ounces. For the questions that follow, suppose that the company is telling the truth. All right, so 12 ounces of soda with a standard deviation of 0.4 ounces. These are your population parameters. All right, it's the population mean and it's the population standard deviation. So those right there are the population parameters, specifically the mean and the standard deviation. All right. What additional information would you need to calculate the probability that a single randomly selected can contains 11.9 ounces or less? Now assume that it's true. What is the probability? All right. So to be able to calculate that, you would need to know that the population is normally distributed. All right. Without knowing that information, we can't use NCDF. And this problem doesn't tell us that it is. So that's the missing piece of information that we'd have to know. All right. Once we do know that, then we can just use our NCDF and we can say, all right, what are the odds of getting below 11.9 when the mean is 12 and the standard deviation is 0.4? All right. So bring up NCDF. We're doing negative 9999 to 11.9 when the mean is 12, the standard deviation is 0.4, and we end up with 0.4013. All right. So that's the odds of getting a single can that's 11.9 ounces or less. Now let's take a look at B here. A quality control inspector measures the contents of an SRS of 50 cans. So this is our N. Of the company soda and calculates the sample mean. What are the mean and standard deviation of the sampling distribution of X bar for sample size is of N equals 50? So that's saying the mean of X bar. If you were to calculate a whole bunch of samples of size 50 and get those means, what would they average out to be? Now again, this always just works out to be the population mean, which they give us in the problem as 12. Right? The standard deviation of X bar, we have to use our formula, which is this population standard deviation divided by the square root of N. So that leaves us with 0.4 divided by the square root of 50, which if we do that, 0.4 divided by the square root of 50 is 0.0566. So 0.0566. The inspector in part B obtains a sample mean of 11.9 ounces. Collect the probability that, calculate the probability that a random sample of 50 cans produces a sample mean of 11.9 ounces or less. Be sure to explain why you can use the normal calculation here. All right, So let's take a look at what we've got going on here. I probably should have stated here. The reason we can do this is because even though we're sampling without replacement, sample is less than 10% of population. All right. So again, when you're sampling without replacement, it's important that your sample is less than 10% of the population. Otherwise, you can't really rely on that standard deviation that you're calculating. Here, explain why we can use the normal calculation. Basically, sample size is above 30. So the sampling distribution will be normal, even if the population is not. Okay. Now, let me just make sure that you have these two straight, because this is where it can sometimes get confusing. This question is asking, what are the odds of getting a single can that is 11.9 ounces or less? This one is asking, what are the odds of having a sample of 50 cans where the average of those cans is below 11.9. All right. So we should expect the probability to be lower. All right. It's not that weird to get a single can that's a little low. It would be weird to get 50 cans that average out to being that low. All right. So let's see what we actually get. We're going to do an NCDF from negative 9999 to 11.9 when the mean is 12. And the standard deviation, because now we're using our sampling distribution, because we're not talking about one can, we're talking about 50 cans averaged together, is 0.0566. And let's see what that gives us. All right, so NCDF, negative 999 to 11.9, 12. The only thing that has to change is this bottom part. And it brings it all the way down to 0.0386. All right, so what would you conclude about whether the company is underfilling its cans of soda? All right, so that's basically saying, what does this actually mean? All right, so this is saying there is only a 3.86% chance of getting a sample mean of 11.9 or less when n equals 50 if the true population mean is 12. All right, so this number is contingent on a lot of things. This 3.86 is contingent on 12 being the true population mean and your sample size being 50. But if both of those things are true, there was only a 3.86% chance of getting this number or lower, which is pretty low. So the company is probably lying. All right. It's more likely that the population mean isn't actually 12 like the company is claiming. It's probably a little smaller, which is why you ended up with this mean of 11.9 when you took your sample. Okay, but these are the two main problems that you have to be able to do. One is taking a look at a situation that is quantitative, using the appropriate formulas to figure out information about your sampling distribution, and then calculating a probability from that sampling distribution. One is looking at more categorical data that deals with generally proportions. Again, using the appropriate formulas, using it inside of an NCDF to get your final answer there. All right. So let me know if you have any questions. Otherwise, best of luck and have a great day. Bye.